In this video, we're going to learn how to determine the pH and pOH of solutions of weak acids and bases. So let's say we have a problem. Determine the pH of a 0.100 molar solution of HCN. Now, if this were a strong acid, then the concentration of H3O plus would be equal to the concentration of HCN, and it would be a simple problem. But since this is a weak acid, it has a very low equilibrium constant, and that equilibrium favors the HCN rather than the dissociated H3O plus and CN minus. So really, the equilibrium is very heavily favoring the left side. Still, we can calculate the amount of product, specifically H3O plus, that does come from HCN dissociating. And we can do that using an ice chart. So initially, we have some HCN at a 0.100 molar concentration, and we don't have any H3O plus or CN minus. This is before any dissociation occurs. We don't know the exact extent of ionization just yet, so what we can say is that the HCN loses some X molarity, and H3O plus and CN minus increase by X. For every bit of HCN that dissociates, we get the same amount of H3O plus and of CN minus that come from it. And at equilibrium, therefore, we have a concentration of HCN that is going to be 0.100 minus X molar, and the H3O plus and CN minus will be both X molar. So from here, we can write the equilibrium expression, and for this reaction, since the HCN is aqueous, the H3O plus and the CN minus are aqueous, but the H2O is a liquid, we can say products, the right side, over the reactants, which only would be the HCN because the H2O is not participating in equilibrium. There's our equilibrium expression. Now, at equilibrium, we can say that the concentration of H3O plus is X molar. That's what we found here. We can also say the concentration of CN minus is X molar, and the concentration of HCN is 0.100 minus X molar. That's the denominator. Now, what we can say from here is that there's an approximation that we can make. Because this equilibrium very heavily favors the left side, we can say that X is not going to be very much. The reaction doesn't go forward very much. And as long as we have a reasonable concentration of HCN, 0.1 molar is plenty, we can say that X is going to be very small relative to this 0.1. So what we can do is say that 0.100 minus X is really just about 0.100. And that makes the math a lot easier here. So from here, we can replace Ka with what we know it to be, which is 6.2 times 10 to the negative 10th. And so that equilibrium constant equals X squared, H3O plus times Cn minus, divided by the HCN concentration, which is still approximately 0.1. From here, we can get rid of the 0.1 on the denominator. We get to 6.2 times 10 to the negative 11th is equal to X squared. Take the square root of both sides, and we get that X is equal to 7.9 times 10 to the negative 6th. This is a molarity, and that is the molarity of, apparently, the H3O plus and the Cn minus at equilibrium. But since we're looking for pH, the only thing that really matters is the H3O plus concentration, which we know. So we can say that the negative log of the concentration of H3O plus, the negative log of this, is equal to pH. And what we end up getting is that the pH is equal to 5.10. And note that for our weak acid, HCN, at a 0.1 molar concentration, well, we get a mildly acidic solution. It's under 7, the pH. It's 5.10. Note that for the 2 sig figs in the log, we have 2 decimal points. A similar procedure could be solved for determining pH of a 0.200 molar solution of NH3, NH3 being a weak base. And I'm going to walk through this pretty quickly because it's basically the same thing. We set up our equilibrium equation. We have the NH3 is aqueous, it reacts with water, and instead of getting H3O plus, we have OH minus because the NH3 is acting as a base. NH4 plus is the conjugate acid. And initially, we have a 0.2 molar solution of NH3 with no hydroxide or ammonium, but some amount of ionization occurs, and we end up with 0.2 minus X. We get X molar hydroxide and X molar ammonium. We can bring this over to a Kb equation. The equilibrium constant Kb is equal to the concentration of products on the right side over reactants on the left. We omit the water. Note that at equilibrium we have X and X as our hydroxide and ammonium concentrations over 0.2 minus X molar for the reactant side, the NH3. But because the X is going to be small, we will say that this simplifies to approximately X squared over 0.2. And from here, same as before. We can bring the 0.2 over and multiply that 0.2 by both sides. We end up getting, and then taking the square root, we end up getting 1.9 times 10 to the negative third molar is X. Now, for clarity, that is the concentration of OH minus as well as NH4 plus. But the concentration of OH minus is actually useful to us because that is going to get us to the pOH. pOH is the negative log of the concentration of hydroxide that we found. And that comes out to 2.72. And then from there, we can just say that pH plus pOH is equal to 14. So 14 is equal to 2.72 plus pH, and therefore pH is going to be equal to 14 minus 2.72. It's 11.28. Again, I went through this one rather quickly because it's essentially the same as the first problem. But here's just another way of looking at a sort of weak acid or weak base problem. So I hope this video has been helpful. Please leave any questions or comments in the comment section below. Thanks for watching.